Imagine you're standing on the side of a jagged, just completely chaotic mountainous landscape, and you're totally blindfolded.
Right. Not a great hiking scenario.
No, definitely not. But your only goal, your entire mission, is to find the absolute lowest valley in this terrain. And your only tool to do this is just feeling the slope of the ground directly under your boots.
Right.
Yeah, take that image, but imagine this isn't a normal three-dimensional mountain. It's a landscape with tens of millions of dimensions.
Yeah.
Incredibly disorienting, just massive mathematical geometry. That is the exact reality of training a deep neural network.
Yeah, it really is a profound shift from how we normally think about software. Usually a computer program is just a set of clean deterministic instructions.
Right, like an if-then statement.
Exactly. You write the rule, the computer executes it. But in machine learning, we don't write those instructions. We set up an architecture, we feed it data, and we force it to navigate that massive, murky landscape of probabilities until it figures out the instructions for itself.
Which is wild. So we are so glad to have you, the learner, joining us for this deep dive. Our mission today is to crack open that black box.
Yes, definitely.
We're diving into a highly technical stack of materials covering the optimization algorithms, the mathematical architectures, and the specific implementation details that take a neural network from a state of complete random ignorance to a highly accurate predictive model.
And we're really moving past the abstract metaphors today. We are looking at the foundational mechanics here.
Right, the real math.
Yeah, the calculus of how a model actually updates, the structural algorithms used to prevent memorization, and the precise optimization paths of modern techniques like the atom optimizer and snapshot ensembles.
So if you've ever wondered why an AI algorithm actually learns instead of just, endlessly crunching numbers to no avail, we're going to unpack the exact math and architecture that makes it possible.
It's a lot to cover, but it's fascinating stuff.
It really is. So let's start at the very bedrock of this whole process, the update rule, the algorithm that tells our blindfolded hiker which way to step.
Right.
In the source material, the baseline is established as vanilla gradient descent, or specifically stochastic gradient descent, which usually gets abbreviated to SGD.
Yeah, SGD. And that algorithm is really the engine of all modern deep learning. Conceptually, it's calculating the error or the loss of the network's current predictions.
Okay.
And it's figuring out how to tweak the internal parameters, the weights, to make that error smaller.
So looking at the basic code snippet provided in the text, it defines this pretty simply. It says, the new weights equal the old weights minus a step size multiplied by the gradient of the weights.
Exactly.
Okay, let's translate that math for the listener. The gradient is essentially the slope, right? It's the direction of steepest descent.
Yes, steepest descent, meaning going up.
Right, so if we want to go down to the valley of lowest error, we multiply that slope by a negative. We take a step in the exact opposite direction of the steepest upward slope.
Correct. But the critical implementation detail here is the word stochastic.
Right, stochastic.
Because in a purely theoretical, perfect scenario, if you wanted to know the exact true slope of your entire lost landscape at your current position, you would have to calculate the error for every single piece of data in your training set simultaneously.
Oh, wow. So if I'm training an image recognition model on, say, 10 million photographs, I'd have to push all 10 million photos through the network.
Yep.
Calculate the error for each one, average them out, and then take one single microscopic step down the mountain.
Exactly. And then you would have to do it all over again for the very next step.
That sounds impossible.
It practically is. The computational cost of that is astronomical. The memory bandwidth required to process a full batch of 10 million high-resolution images for a single update, it just exceeds the capacity of modern hardware.
Wow. Okay, so we can't do that.
No. So instead of full batch gradient descent, we use stochastic gradient descent with mini batches.
A mini batch being a tiny fraction of the data, like maybe 32 images or 128 images at a time.
Yes. You randomly sample a mini batch, push it through, and calculate the gradient based only on those 32 images.
Okay, but doesn't that mess up the slope?
Well, yes. What this does mathematically is inject a massive amount of noise into the optimization path. You are not getting the true gradient.
Right.
Sometimes the mini batch of 32 images happens to contain, unusual data, and the calculated slope points slightly left of the true minimum. The next batch might point slightly right.
But over thousands of steps, those little left and right errors cancel each other out.
Right.
Right? And the general trend points you downward.
Exactly. It's computationally necessary because we physically cannot run the full data set, but it means our blindfolded hiker is acting on slightly faulty information at every single step.
Which brings us to the first major mathematical hurdle outlined in the research. What happens when the underlying geometry of the landscape is fundamentally hostile to this kind of noisy, step-by-step descent?
Yeah, this is where it gets tricky.
The texts refer to this as the problem of high condition numbers. Now, a condition number, I'm assuming we're talking about the shape of the terrain here, but what does that actually measure?
It measures the ratio of curvature in different directions. And to understand this, we have to look at the Hessian matrix.
Okay, the Hessian matrix.
Yeah. If the first derivative, the gradient, tells you the slope, the second derivative tells you the curvature. It tells you how fast the slope itself is changing.
Oh, I see.
The Hessian is basically the square matrix of all the second-order partial derivatives for every parameter in the network.
Okay, so if the first derivative is our velocity, the second derivative is our acceleration.
That is a very functional way to think about it, yeah. The Hessian matrix has mathematical properties called eigenvalues.
Eigenvalues, right.
And these represent the magnitude of this curvature in each specific dimension of the landscape. So a high condition number occurs when there is a massive discrepancy between the largest eigenvalue and the smallest eigenvalue.
Let's visualize that. If I have a high condition number, it means in one dimension, the slope is changing incredibly fast.
Right.
But in another dimension, the slope is changing incredibly slowly.
Exactly. Picture a steep, narrow ravine. If you look across the ravine from one wall to the opposite wall, the terrain goes up sharply, high curvature.
Yeah.
But if you look along the floor of the ravine, sloping gently down toward the distant valley, the terrain is almost flat, low curvature.
I can see how that completely destroys the algorithm. If my update rule just says, take a step in the direction of the steepest downward slope, and I'm standing on the side of this ravine.
The steepest direction isn't pointing gently down the valley floor.
Right. The steepest direction is pointing straight down the ravine wall.
Exactly. And because you take a discrete mathematical step dictated by your learning rate or step size, you don't just gently slide to the bottom.
Oh, you overshoot.
You do. The algorithm calculates that steep downward slope, takes a large step, and ends up overshooting the floor entirely, landing high up on the opposite wall of the ravine.
Then it recalculates, sees a steep slope pointing back the other way, and takes another huge step.
Yep.
It just ricochets back and forth across the ravine walls, zigzagging wildly, while making virtually zero progress along the flat bottom toward the actual minimum.
It is a devastating inefficiency. It's burning through computational cycles and getting nowhere. But ravines are not the only topological traps. The materials highlight an even more complex geometric problem in high-dimensional spaces.
Saddle points.
Saddle points.
Now, a local minimum is a concept I think is fairly intuitive. You're walking down a mountain, you step into a small crater, and suddenly every direction is pointing up. The algorithm stops because the gradient, the slope, is zero.
Right.
But a saddle point, if the slope hits zero, doesn't that inherently mean we're at the bottom of something? How can you be flat but not at the bottom?
Think of the physical shape of a horse saddle.
Okay.
If you sit in the center of the saddle and move forward or backward toward the horse's head or tail, the shape curves upward.
Right, it goes up.
But if you move left or right down the sides of the horse, the shape curves downward.
Oh, wow. Okay.
So the exact center of that saddle is completely flat. The gradient is zero.
It's a mix of curvatures depending on which dimension you're looking at. But if the gradient is zero at that exact microscopic center point, the update rule multiplies by zero. The weights stop updating. The model halts.
Yes.
But realistically, what are the odds of our noisy, stochastic algorithm landing on that one exact flat pixel in a landscape of millions of parameters?
The odds of landing directly on the mathematical center are vanishingly small. But the center itself isn't the real problem.
It's not.
No, the danger lies in the geometry surrounding the saddle point. In a neural network with millions of dimensions, these saddle structures create vast, expansive plateaus. As the optimization algorithm approaches this region, the slope becomes incredibly gentle.
So the gradient gets smaller, which means that the steps the algorithm takes get smaller and smaller.
And because the steps are so tiny, it takes an agonizingly long time to traverse that flat plateau before it finally reaches the edge where the landscape curves downward again. It slows the training process to an absolute crawl.
Wow.
When you combine the zigzagging of ravines with the stalling of saddle plateaus, you realize that vanilla SGD, while, elegant, is often insufficient for deep architectures.
We need a way to fix the math. Which leads us to the concept of second-order methods versus momentum.
Right.
If our problem is that the first derivative, the slope, is tricking us into bouncing off walls, why don't we just use the second derivative, the curvature, to map the exact shape of the ravine and calculate the perfect path down the middle?
From a purely theoretical standpoint, that is the ideal solution.
Yeah.
If we have full knowledge of the curvature via the Hessian matrix, we don't have to guess. We can calculate the exact location of the minimum in a single step. The texts detail the Taylor expansion approximation used to derive this.
Okay, let's break down the mechanics of that Taylor expansion for the listener without, getting lost in the raw math formatting.
Sure. The underlying logic of the equation is about projecting a future position based on current information. It estimates the loss at a new position by taking the loss at your current position, adding the linear change indicated by the gradient, and then adding a quadratic penalty or boost dictated by the Hessian matrix.
So if I'm trying to predict where a car will be in 10 seconds, I take its current location, add its current speed, and then factor in whether the driver is pressing the gas or the brake the acceleration.
Exactly.
By mapping all three, I can pinpoint the destination.
That captures the essence perfectly. And from that expansion, we derive the theoretically optimal update rule. Instead of taking a step determined by an arbitrary learning rate, you multiply the gradient by the inverse of the Hessian matrix.
Okay, the inverse.
Yeah, and this completely neutralizes the ravine problem. The math automatically scales down the step size in the direction of high curvature, the ravine walls, and scales up the step size in the direction of low curvature, the valley floor.
It sounds like the silver bullet. It points the algorithm straight down the valley. So why isn't every machine learning engineer on the planet using this to train their models right now?
Because of the harsh reality of computational complexity.
Oh, right.
Inverting a matrix is an incredibly demanding mathematical operation. The complexity scales at big O of n cubed, where n is the dimension of the matrix.
Meaning if the matrix is 10 times larger, it takes 1,000 times more compute to invert it.
Yes. Now, consider a modern deep neural network. Even a relatively small model might have 1 million parameters.
Okay.
The Hessian matrix for that model is a grid of 1 million by 1 million. That is 1 trillion elements.
And computing the inverse of a 1 trillion element matrix.
It would require on the order of 10 to the power of 18 operations for a single step of training. And you have to do this thousands or millions of times. It just exceeds the memory capacity and processing power of our largest GPU clusters.
It's just not possible.
No. The texts do mention workarounds, like quasi-Newton methods such as BFGS, which try to approximate the inverse Hessian without actually calculating the full matrix. But even these approximations are too memory-intensive for modern deep learning architectures.
So we want the stability and the insight of the second derivative,
Hmm.
but we absolutely cannot afford the compute budget to calculate it.
Exactly.
We need a hack. We need a way to smooth out the zigzags without building a trillion-element matrix. And the practical solution to this is borrowing a concept from physics momentum.
Momentum is a brilliant, computationally cheap algorithmic data flow. Instead of relying solely on the gradient at the current time step, we track a moving average of all the past gradients.
Okay.
We essentially accumulate a velocity vector. When it's time to take a step, we combine our current slope with our accumulated momentum.
The classic analogy here is a snowball rolling down a hill. As it rolls, it gathers mass and speed. If it hits a tiny flat spot or a small localized crater, it doesn't just stop. The momentum it built up on the long descent carries it right over the lip of the crater, allowing it to continue down the mountain.
It's particularly effective in those high condition number ravines. Think about the zigzagging. The gradient is pointing sharply left, then sharply right, then sharply left.
Yeah.
If you average those directions over time, the left and right vectors mathematically cancel each other out. But the small component of the gradient that is pointing down the valley floor is consistent.
Oh, so that consistent direction compound.
Exactly. The momentum algorithm dampens the useless oscillations and accelerates the progress along the true path.
It builds a memory into the system. But the source material highlights an evolution of this concept that takes it a step further. Nesterov accelerated gradient, or NAG. What is the implementation difference between standard momentum and Nesterov?
It comes down to the order of operations. With standard momentum, you stand at your current position, you calculate the slope, and then you add your stored velocity to figure out where to step next.
Okay.
Nesterov flips that logic.
How so?
Well, Nesterov recognizes that we already know a large portion of our next step, which is the momentum vector. we're already committed to moving in that direction. So mathematically, Nesterov applies the momentum first.
It moves first.
Yeah, it takes a look-ahead step to a projected future position. Only then, at that future position, does it calculate the gradient to make a final correction.
Okay, let's ground that. Think of a race car driver entering a sharp curve. A novice driver, representing standard momentum, is looking right at the hood of the car. They realize the slope of the track is changing, they realize they have too much forward velocity, and they slam on the brakes, but it's too late. The momentum carries them into the wall.
Right, they overshoot.
But the Nesterov driver is looking ahead through the apex of the curve. Because the algorithm calculates the gradient at the projected future position, it detects the upcoming change in a landscape before it fully commits.
Exactly. If the momentum is about to carry the algorithm up the opposite wall of a ravine, the look-ahead gradient detects that upward slope and immediately generates a negative vector to pull back, preventing the overshoot.
It's highly responsive.
Okay.
It gives us much more stable convergence without the big O of n-cubed nightmare of calculating the Hessian.
Yeah, it's a huge improvement.
But even with Nesterov, we are still dealing with a fundamental limitation. We have a single global learning rate. We are taking roughly the same size step for every single parameter in the model.
Which is a severe bottleneck when dealing with sparse data or highly complex architectures. In any real-world dataset, some features are ubiquitous and some are incredibly rare.
Let's use image recognition. If the model is trying to identify cats, the parameters that recognize basic fur textures are going to trigger on almost every single image. They are constantly receiving gradient updates. But the parameters tasked with identifying, say, a very specific shape of a bell on a collar might only see a useful signal once every 1,000 images.
And if you apply a single static learning rate to both of those parameters, you force a compromise.
Because they need different treatment.
Exactly. If you set the learning rate high enough for the rare collar parameter to learn quickly, that same high learning rate will cause the fur parameter to update so violently that it overshoots and zigzags out of control.
Right.
But if you lower the learning rate to stabilize the fur parameter, the collar parameter gets updated so microscopic that it effectively never learns anything.
So we need a system that can individually tune the step size for every single dimension. And this evolution starts with Adigrad and moves into RMS prop. How do these algorithms actually manipulate the step sizes under the hood?
They mathematically scale the learning rate based on the historical activity of each specific parameter. The algorithmic mechanism involves accumulating the squares of the past gradients.
Let's pause on the math. Why square the gradient?
Squaring it ensures the value is always positive. We don't care if the parameter moved left or right. We only care about the absolute magnitude of how much it has been oscillating.
Oh, I see.
We accumulate this squared history into a variable. Then, when calculating the next step, we take our global learning rate and divide it by the square root of that accumulated history.
This is a brilliant self-regulating loop. If a parameter, like our fur detector, has been updating constantly and wildly, its accumulated history is a massive number.
Right.
We take our learning rate and divide it by that massive number. The resulting step size shrinks drastically. The math acts as an automatic dampener for frequently updated weights.
Conversely, the rare color parameter has almost no historical movement. Its accumulated history is tiny. Dividing the learning rate by a tiny number effectively preserves or boosts the step size, allowing it to take meaningful leaps when it finally sees relevant data.
That's incredibly smart.
And for numerical stability, the code adds a microscopic an epsilon, like 10 to the negative eighth to the denominator, to ensure the algorithm never accidentally divides by 0 and crashes.
So RMS prop handles the dynamic scaling. But the undisputed king of modern deep learning optimization is the ADAM optimizer. The texts essentially deconstruct ADAM as the ultimate hybrid of everything we've talked about so far.
ADAM stands for Adaptive Moment Estimation. It merges the benefits of momentum with the adaptive scaling of RMS prop.
Okay, so it's doing both.
Yes. It maintains two separate moving averages for every parameter. The first moment is the mean of the gradients. That's our Nesterov-style momentum pushing us over saddle points.
Right.
And the second moment is the uncentered variance of the gradients. That's our RMS prop-style scaling factor adjusting the learning rate.
It's doing both jobs at once. And it relies on a very specific set of default hyperparameter constants that have become almost universally standard.
Yeah, the default values dictate how fast these moving averages decay. The decay rate for the first moment, called beta 1, is usually set to 0.9. The decay for the second moment, beta 2, is typically 0.999.
Okay.
Combined with a standard base learning rate of 0.001, ADAM is incredibly robust across a massive variety of neural network architectures right out of the box.
But there's a very specific, fascinating mathematical trick hidden inside the ADAM algorithm called bias correction. I want to dig into this because it highlights how delicate these systems are when they first wake up. What is the bias we are correcting?
The bias is a direct result of how computer memory is initialized. When you start training on step 0, the model has no history. The moving average vectors for the first and second moments are initialized as arrays of pure zeros.
The snowball hasn't started rolling down the hill yet. It has zero momentum.
Now, look at how the moving average updates on the very first step. If beta 1 is 0.9, the formula calculates the new momentum by taking 90% of the old momentum and adding 10% of the current gradient.
Right.
But because the old momentum is 0, 90% of 0 is 0. The new momentum is simply 10% of the current step.
Oh, so even though the gradient might be huge, the algorithm mathematically squashes it down to a tenth of its actual size. The system is heavily biased towards 0 because of those initial empty arrays.
Exactly.
If it just kept running like that, the model would barely move off the starting line. It would stall out before it even got going.
To solve this, the designers of ADAM introduced a time-dependent mathematical correction. At every step, the moment estimates are divided by a decay factor based on the current time step, t.
Okay.
The exact formula for the first moment is to divide it by 1 minus beta 1 to the power of t.
Let's run the numbers on that to see how the math evolves over time. At step 1, t equals 1. Our beta 1 is 0.9. So we are dividing by 1 minus 0.9 to the first power, which is 0.1.
And dividing any number by 0.1 is mathematically identical to multiplying it by 10.
Wow. So on step 1, the algorithm takes that artificially squashed momentum, which was only 10% of its true size, and multiplies it by 10, restoring it to its full magnitude. It artificially boosts the signal to counter the zeros.
But the true elegance is what happens as the training progresses. Let's fast forward to step 1000. T equals 1000. Now the denominator is 1 minus 0.9 to the power of 1000.
And 0.9 to the power of 1000 is an infinitesimally small number. It's virtually 0. So the denominator becomes 1 minus 0, which is just 1.
Right.
And dividing by 1 does absolutely nothing.
Precisely. As the true historical data accumulates and the zero initialization bias naturally fades, the bias correction mathematical term smoothly and automatically self-destructs. It's a beautifully engineered solution.
It's a temporary booster rocket that falls away once the model reaches orbit. Now, given all this incredible automated machinery inside ADAM, there is a counterintuitive, practical takeaway in the source materials.
Oh, yes.
While ADAM is the safest, most reliable optimizer to use blindly, a highly skilled engineer using just basic SGD with momentum can often achieve a better final accuracy. How is that possible? If ADAM is so smart, why would we go back to the basic snowball?
Because ADAM's greatest strength, its dynamic per-parameter scaling, can sometimes be its greatest weakness.
How so?
By constantly monitoring and throttling down the learning rates of parameters that move frequently, ADAM can be too aggressive. It can prematurely shrink the step sizes before the model has found the absolute deepest part of the Lost Valley. It essentially settles for a good enough local minimum because it mathematically convinced itself to stop exploring.
It's the difference between driving a car with an automatic transmission versus a manual.
That's a great analogy.
ADAM is the automatic. It shifts gears for you, it prevents you from stalling, and it guarantees you will get to your destination safely with very little effort. SGD with momentum is the manual transmission. If you don't know what you're doing, you will grind the gears and crash.
Yes, you will.
But if you have the patience, the skill, and the compute budget to manually tune the learning rate decay schedule, aggressively managing exactly when and how the step size drops over time, you can force the algorithm deeper into the valley. You can squeeze a slightly higher final performance out of the architecture.
It requires deep intuition about the specific loss landscape of your dataset. But yes, it remains a standard practice in state-of-the-art computer vision models for exactly that reason.
But finding the deepest part of the valley is only half the battle. Because you could find the absolute perfect mathematical minimum, but if the model is just memorizing the training data, the whole exercise is pointless.
Completely pointless, yes.
This brings us to a massive shift in our strategy: structural regularization. We have to alter the actual architecture of the network during training to prevent it from cheating.
What you're referring to is overfitting. A deep neural network has millions of parameters, which gives it an immense capacity for memorization.
Right.
Instead of learning the general abstract features that define a cat pointed ears, whiskers, specific eye shapes, it has enough memory to simply memorize the exact pixel arrangements of the 10,000 cats in your training set.
So when you show it a photo of a new cat it has never seen before, sitting in slightly different lighting, the model completely fails because it hasn't learned the concept of a cat. It just memorized a spreadsheet of pixels.
To combat this, we use regularization algorithms. And the most prominent structural tool is dropout.
Dropout, okay.
The mechanism is simple but radically destructive. During every single forward pass of the training data, the algorithm randomly selects a percentage of the neurons in a layer and sets their output to 0. It literally turns them off. The probability of a neuron being dropped, denoted as p, is typically set around 0.5 or 50%.
It's like making a professional basketball team practice. But every single day, the coach randomly blindfolds half the players on the court. The players don't know who is going to be blindfolded until the whistle blows.
That analogy captures the intent perfectly. It prevents what we call co-adaptation. In a standard network, neurons can become overly reliant on each other.
Okay, so like passing the ball to the star player.
Exactly. Neuron A might only learn to fire correctly if neuron B is also firing and passing it a specific signal. They form a fragile, localized circuit that only works on the training data.
But with dropout, neuron A can never rely on neuron B, because half the time neuron B doesn't exist. Neuron A is forced to become a robust, independent feature detector that provides value regardless of what the rest of the network is doing.
Exactly.
Every single player on the court has to learn how to shoot, pass, and defend independently, because they can never rely on the star point guard to bail them out.
And the mathematics of this process generates staggering complexity. The sources highlight the combinatorics of dropout on a standard fully connected layer. Let's say a layer has 4,096 neurons.
Okay.
Because each individual neuron can independently be either turned on or turned off during a pass, the number of possible structural configurations for that single layer is 2 to the power of 4096.
2 to the power of 4096. Let's quantify that. That is roughly 10 to the power of 1233 possible subnetworks.
To ground that number, the observable universe, every star, every galaxy, every planet we can perceive, contains roughly 10 to the power of 82 atoms.
10 to the power of 1233 is a number so absurdly vast it defies physical reality. What this means is that every single time you push an image through the network during training, a random number generator builds a completely unique architecture.
Yes.
Across millions of training steps, you will never, ever train the exact same subnetwork twice.
You are effectively training an incomprehensibly massive ensemble of slightly different models simultaneously, all of which are sharing the same underlying weight matrices. It forces the weights to be highly generalized.
But this introduces a massive structural paradox when we finish training and try to actually use the model in the real world.
Right, the inference phase.
During inference, when a user uploads a photo from their phone, we aren't running dropout anymore. We need the network to give us its best, most stable prediction. But if the network spent its entire life training with half its neurons turned off, what happens when we suddenly plug all 4096 neurons in at once?
The math breaks. Or rather, the electrical scaling of the activations completely explodes.
Really?
Yeah, the downstream layers of the network have spent weeks adapting to a specific magnitude of incoming signal. If you suddenly double the number of active neurons, the raw sum of those signals doubles.
It would be like a factory expecting 50 boxes of parts per hour on a conveyor belt, and suddenly 100 boxes start pouring down the belt. The system jams.
Precisely. To solve this, there is a mandatory scaling factor applied during inference. The expected value of a neuron's activation must remain constant between training and deployment.
Let's walk through that expected value calculation.
If the probability of keeping a neuron active during training is p equals 0.5, then the expected output of that neuron is 50% of its maximum potential signal. Half the time it sends its full weight, half the time it sends 0.
Right.
Therefore, during inference, when the neuron is active 100% of the time, its raw output must be mathematically multiplied by p. You multiply the output by 0.5.
You essentially turn the volume knob down by 50% on every single neuron. The factory line slows the belt down so only 50 boxes arrive per hour.
Exactly.
The downstream layers receive the exact same average signal strength they learned to process during training. It's a remarkably simple mathematical fix for such a massive structural disruption.
So we have manipulated the physical architecture to prevent memorization. But the materials point to another equally vital strategy: data augmentation.
Right. Changing the data itself.
If the model is memorizing the specific pixels of the training data, one solution is to simply never show it the exact same image twice. We program algorithmic data flows to constantly mutate the inputs.
If you don't have enough data, just mathematically manufacture more. The standard pipeline utilizes geometric and color matrix transformations. Every time an image is loaded, a library like Albumentations or InGog applies a randomized set of operations.
Yeah.
It might horizontally flip the image, rotate it 15 degrees, stretch it, shear it, or apply a simulated lens distortion.
The mathematical objective here is invariance. Model must learn that a cat is still a cat regardless of its orientation in space. By constantly applying these affine transformations, we force the network to abstract the core geometry of the object, rather than memorizing the specific array of pixels in a static photograph.
The sources detail the exact, precise augmentation pipeline used to train ResNet, which is one of the most famous and foundational architectures in deep learning history. It's a highly specific three-step algorithmic flow. Step 1. Choose a random integer, L, between 256 and 480. Step 2. Resize the original image so that its shortest side is exactly equal to L pixels. Step 3. Extract a random 224 by 224 pixel square from that newly resized image. Why this specific multi-layered scaling process?
It is a deliberate strategy called multiscale training. By randomizing the scaling factor L before extracting the fixed 224 pixel crop, the algorithm drastically alters the physical scale of the features within the crop.
Right, because if L happens to be 256, the image isn't scaled up that much. The 224 pixel crop probably contains the entire cat.
But if L is randomly chosen to be 480, the image is massively enlarged. Now, when you take a 224 pixel crop, you might only capture the cat's ear, or an eye, or a patch of fur.
Oh, I see.
The neural network is forced to learn scale invariant features. It has to be able to identify a cat whether the camera was 5 feet away or 5 inches away.
It's an incredibly robust way to squeeze every drop of geometric information out of a limited data set. But then the source material introduces an augmentation algorithm called mix-up.
Mix-up is fascinating.
And this technique, it fundamentally breaks the logic of how we categorize data. We aren't just rotating a cat, we are mathematically blending it with other things.
Mix-up is a beautiful subversion of traditional classification logic. Instead of applying matrix transformations to a single image, mix-up pairs two completely random, unrelated images from the dataset. It then performs a linear interpolation, a weighted average of their pixel arrays.
Let's visualize this. The algorithm grabs a photo of a cat and a photo of a dog. It generates a random weighting ratio, say 0.4 and 0.6.
Right.
It then goes pixel by pixel. It multiplies the color value of the cat pixel by 0.4, multiplies the dog pixel by 0.6, and adds them together.
Yes.
The resulting image is a ghostly, semi-transparent hallucination where you can faintly see a cat superimposed directly over a dog.
Visually, it looks like a mistake. But the true genius of mix-up isn't just blending the input pixels, it is blending the target labels.
This is where I struggle. If I show a human child that ghostly cat-dog image and ask, "What is this?" they'd be confused. How does the loss function mathematically evaluate an image that doesn't actually exist in the real world?
We have to look at how loss functions traditionally operate. Standard classification uses one-hot encoded vectors. A network predicts absolute certainties. A cat label is mathematically represented as a vector of 1, 0. A dog is 0, 1.
Okay.
There is a hard mathematical cliff between the two categories. The network is penalized heavily if it isn't 100% confident.
Which encourages the model to become overconfident even when it shouldn't be.
Exactly. But with mix-up, because the input image is 40% cat and 60% dog, the ground truth target vector is also interpolated to match. The loss function is now optimized to predict the vector 0.4, 0.6.
Ah, so we are forcing the neural network to output uncertainty. We are demanding that it learn a smooth, linear transition between categories rather than a hard cliff.
It drastically regularizes the decision boundary. Without mix-up, networks tend to draw highly jagged, complex geometric borders between classes in the high-dimensional space, which leads to wildly confident incorrect predictions when a new image lands just on the wrong side of the line.
Mix-up irons out those wrinkles.
It forces the network to map the space linearly. If an image is a 40% blend, the confidence must be exactly 40%. It creates a much more rational, calibrated model that is highly resistant to confusing or adversarial real-world data.
Okay, so let's step back and look at the control panel we built. We're hacking the internal architecture with dropout combinatorics. We are hacking the data inputs with multi-scale crops and mix-up. We're hacking the gradient descent with Nesterov momentum and Adams adaptive learning rates.
That's right.
But someone has to actually dial in the settings for all these systems. This brings us to hyperparameters, ensembles, and the overarching architectures of transfer learning.
The source material uses the excellent analogy of a DJ mixing desk. A machine learning engineer has to set the dials before the music even starts. What is the base learning rate? What is the beta 1 momentum decay? What is the dropout probability P? What is the batch size?
These are all hyperparameters.
Yes, variables that govern the learning process itself rather than the internal weights the model learns.
And finding the optimal combination of these dials is a massive optimization problem of its own. You can't just guess. You have to systematically search the hyperparameter space. The text contrasts two primary methods for this: grid search and random search.
Grid search is the traditional intuitive approach. If you have two dials you want to tune, say, learning rate and dropout, you select a few discrete values for each: low, medium, and high.
Okay.
You then train a separate model for every single combination. 3 learning rates times 3 dropout rates equals a grid of 9 total training runs.
It sounds thorough. You cover the whole board uniformly. But the mathematical analysis provided in the source definitively proves why random search is vastly superior. Why is the unstructured approach better?
It hinges on a phenomenon common in high-dimensional deep learning: the concept of unimportant parameters. In almost any given task, not all hyperparameters impact the final loss equally.
Give me a scenario.
Let's say you are training a model and the learning rate is absolutely critical. A tiny change in the learning rate drastically alters your final accuracy. We call that the important parameter.
Right.
But for this specific data set, changing the dropout rate from 40% to 50% barely changes the outcome at all. It's the unimportant parameter.
Okay, I'm following.
If you use the 3x3 grid search, you execute 9 highly expensive training runs. But because you only selected 3 discrete values for the learning rate low, medium, and high, you only tested 3 variations of the dial that actually matters. You tested the high learning rate 3 different times, just paired with different irrelevant dropout rates.
Oh, that's a massive waste of compute. You spent 9 runs, but you only generated 3 useful data points about the curve of the important parameter.
Exactly. Now compare that to a random search. You still execute 9 training runs, but instead of a rigid grid, you randomly scatter the 9 coordinate pairs across the 2D search space. Because the coordinates are generated randomly, it is statistically highly improbable that any 2 points will share the exact same learning rate.
So you end up testing 9 completely distinct, unique values for the important parameter. You map the continuous curve that hyperparameters affect much, much more tightly, yielding a far better optimization for the exact same computational cost.
It is a simple, elegant application of probability that saves thousands of hours of GPU time. But even with perfectly tuned hyperparameters, a single model has limitations. It will always settle into one specific local minimum in the loss landscape, meaning it will have specific blind spots.
Which leads to the concept of ensembles. The text notes that standard ensembling, which is training 5 completely independent models from scratch and mathematically averaging their final predictions, reliably yields about a 2% accuracy boost over any single model.
It relies on the statistical principle of uncorrelated errors. Because each model initializes randomly and walks a different path down the mountain, they will settle in slightly different values.
Okay.
Model A might be incredibly good at identifying orange cats, but struggles with black cats and low light. Model B might be great at black cats, but fails on orange ones.
So when Model A makes a confident mistake, Model B, C, D, and E outvote it. The average prediction smooths out the individual geometric blind spots.
Yes.
But training 5 deep neural networks from scratch, if we're talking about massive models that take weeks to train on a supercomputer, multiplying that cost by 5 is financially impossible for most teams.
That financial constraint birthed one of the most clever algorithmic hacks in optimization theory: snapshot ensembles using a cyclic learning rate schedule. It allows you to build an ensemble of diverse models for the computational price of a single training run.
Okay, a cyclic learning rate. Thus far, we've only talked about the learning rate decaying over time. It gets smaller as we get closer to the bottom of the valley so we don't overshoot. How do you cycle it?
You mathematically force the learning rate to behave like a wave. often using a cosine annealing function. The algorithm starts with a high learning rate, rapidly exploring the landscape, and then smoothly decays it to near zero. Just like normal, the model settles deep into a local minimum.
And once it settles, you take a snapshot. You save the exact configuration of all the millions of weights to your hard drive. That's model 1 of your ensemble.
But here is the trick. Instead of stopping the training, you mathematically force the learning rate to violently spike back up to its maximum value.
You deliberately inject a massive amount of kinetic energy back into the system. You kick the snowball out of the valley.
Exactly. The sudden massive step sizes shatter the model's convergence. It leaps out of the local minimum and goes wildly bounding across the high-dimensional landscape again. Then the cosine function kicks in, the learning rate smoothly decays, and the model settles into a completely different local minimum in another region of the landscape.
And you take another snapshot, model 2. You repeat this cycle, bouncing around the mountain range, settling down, taking a picture, and blasting off again. Because each snapshot represents a different valley, the models make different types of errors. You average them together, and you get the robust 2% accuracy boost of an ensemble. But you only pay the compute cost of running the optimization algorithm once.
It's a masterclass in exploiting the topography of the lost landscape rather than fighting it. But all of these techniques, ensembles, cyclic learning rates, dropout combinatorics, assume you are starting from a random initialization. And in modern applied deep learning, starting from scratch is actually quite rare.
Which brings us to our final architectural discussion, transfer learning. If you want to build a model to detect a specific type of manufacturing defect on an assembly line, you don't generate random noise and train for weeks. You take a massive, pre-trained model, like a ResNet trained by Google, on the ImageNet dataset of 13 million general photographs, and you adapt it.
The foundational logic of transfer learning is that the internal layers of a deep neural network operate as a hierarchical feature extraction pipeline. The very first layers of the network, closest to the raw image, don't know what a cat or a dog is.
Right, they're too simple.
They only learn mathematical representations of basic geometry. Vertical edges, horizontal edges, color gradients.
And the next layers combine those edges to find textures or curves, and the deeper layers combine those into complex shapes like wheels or eyes or ears. Finally, the very last layer, the linear classifier, looks at all those shapes and outputs the final label.
Because those early layers are just learning universal geometry, they are highly valuable for almost any visual task. The source material provides a highly specific matrix for how to manipulate data flows during transfer learning, broken down into quadrants based on two variables: the size of your new data set and how similar your new data is to the original ImageNet data.
Let's analyze these quadrants because this is the practical blueprint for anyone actually deploying AI. Quadrant 1. You have very little data, maybe just a few hundred images, but your data set is very similar to the original training data. Let's say you're trying to classify specific breeds of golden retrievers.
In this scenario, your greatest risk is overfitting. Because you have so little data, if you allow the optimizer to update all the millions of weights in the network, it will instantly memorize your few hundred images and collapse.
So what's the architectural fix?
You freeze the network. You mathematically lock the weights of almost the entire model so the gradient cannot update them. Because your dog images are highly similar to the original dataset, the feature extraction pipeline is already perfectly calibrated to find fur, eyes, and snouts.
Oh, that makes...
You rip off the final linear classifier, the layer that outputs 1,000 different ImageNet categories, and you attach a brand new, randomly initialized linear layer that just outputs golden retriever or not golden retriever.
And then you run your optimization algorithm, your SGD or ADAM, but it only calculates updates for that one single final layer. The rest of the network is just a static filter. It's incredibly fast, requires very little compute, and mathematically prevents the deep network from overfitting.
Precisely. Now, consider quadrant 2. You still have very little data, but your data set is completely different from the original ImageNet photos. For example, you are trying to classify microscopic medical images of cancer cells.
This sounds like a trap. You still have to freeze the network to prevent overfitting on your tiny dataset. But you can't use the deep layers of the pre-trained model because those layers are highly optimized to look for dog ears and car tires. A medical cell doesn't have fur or wheels, so those deep feature extractors will just output garbage.
Exactly. So the structural solution is amputation. You throw away the deep layers entirely. You pull your features from an earlier stage in the neural network.
From the shallow layers.
You keep the first few layers, the ones that learn universal geometric concepts like edges and curves, which are still highly relevant to the borders of a cancer cell. You freeze those early layers, attach your new linear classifier directly to them, and train.
You bypass the highly specific layers entirely. Okay, quadrant 3. You have a massive amount of data, and the data set is very similar, say 500,000 photos of specific dog breeds.
Now the paradigm shifts. Because you have a massive data set, the mathematical risk of overfitting drops significantly. You have enough data to force the network to genuinely learn without memorizing, so you unfreeze or fine-tune the network.
Do you unfreeze all of it?
Usually just the deeper layers. The early layers that detect basic edges are already perfect. Updating them wastes compute. But you unfreeze the last few structural layers alongside your new classifier. You allow the gradient descent algorithm to gently adjust the weights, tweaking the model's understanding of complex shapes to perfectly fit your specific dog breeds.
Which brings us to the final square, quadrant 4. You have a massive data set, and it is completely different from the original. 500,000 microscopic medical cell images.
In this case, you unfreeze and fine-tune a massive portion of the network, potentially all the way down to the first layer. You are fundamentally reshaping the architecture.
But if you're updating the whole network anyway, why not just start from scratch with a random initialization? Why use the pre-trained ImageNet model at all?
Because the pre-trained represent a much more stable, mathematically coherent starting point on the loss landscape than pure random noise.
Oh, I see.
The weights have already self-organized into logical geometric extractors. It provides a massive head start on convergence. However, the source provides a critical optimization warning for fine-tuning regardless of the quadrant. When you unfreeze these pre-trained layers, you must drastically scale down your learning rate.
Why is that? If we want the network to adapt to the cancer cells, shouldn't we let it take big steps?
Think about what a large learning rate does. It generates massive gradient updates. If you blast a fully trained, highly delicate feature extraction network with a massive learning rate, it acts like a mathematical wrecking ball.
Wow.
The huge steps instantly destroy the intricate, finely balanced weight relationships the model spent weeks learning on the original ImageNet data.
You shatter the glass before you can even reshape it.
Exactly. The standard practice is to drop the learning rate to roughly 1/10 or even 1/100th of the rate used to train the original model. You need tiny microscopic updates to gently work the weights toward the new domain without breaking their fundamental structure. It's surgical adaptation, not demolition.
It is incredible how all these pieces fit together. We have covered an immense amount of ground today, and what strikes me is how interconnected all these solutions are. We started with the sheer high-dimensional calculus of the Hessian matrix, trying to map the ravines of high-condition numbers and avoid the sprawling plateaus of saddle points. We saw how the math of momentum and Nesterov's look-ahead hack the physics of the descent to avoid the big O of n-cubed compute bottleneck.
And we traced how the Atom Optimizer further refines that path, using moving averages of variance and the brilliant self-destructing math of bias correction to dynamically scale the learning rate for every single parameter in the network.
From the optimization path, we moved into the structural architecture, detailing the staggering combinatorics of dropout, the 10 to the 1233 possible subnetworks, forcing the model to build robust features, and the necessary scaling math required during inference to prevent electrical overload. We manipulated the geometry of the inputs with multi-scale cropping, and even fundamentally altered the nature of the target labels using the mix-up algorithm to smooth out the decision boundaries.
Finally, we looked at how to control this entire machine from the outside, using the probability mathematics of random search to efficiently map hyperparameter curves, hacking the loss landscape geometry with cyclic cosine annealing to build snackshot ensembles, and carefully navigating the hierarchical feature extraction layers during transfer learning.
Training a deep neural network truly is an intricate, highly deliberate dance of applied mathematics and algorithmic optimization. It's not magic. It's not an unfathomable black box. It is a precise, constructed system.
And understanding these underlying mechanics is what separates someone who just runs code from an engineer who actually understands how to mold the architecture to solve new problems.
But I want to leave you, the learner, with a final puzzle to mull over. We spent a lot of time talking about that DJ mixing desk, We talked about manually creating these cyclic learning rate schedules and hand-tuning Adam's beta parameters and deciding exactly which layers to freeze or unfreeze. It requires a tremendous amount of human intuition and mathematical insight.
It really does.
But as the algorithms themselves get smarter, consider this. What happens when we use a neural network to optimize the hyperparameters of another neural network? Will the math become so abstract, so nested, that the DJ replaces themselves entirely? Can an AI algorithm learn to navigate the high-dimensional loss landscape of building an AI? I highly encourage you to explore the concepts of AutoML and meta-learning on your own. It might just be the next frontier of the mathematical landscape we explored today.
A deeply fascinating structural question to end on.
Until next time, keep diving deep.